Hi, this video is about neutralization reactions. Just a little kind of side note, when you, and this doesn't happen to you guys so much because you're young, but if you get like a stomach ache sometimes, it's because you have too much hydrochloric acid in your stomach, and it's possible that you might take like a Tums or a Rolaids, something that you just chew it and swallow it right away. You're actually taking a base and trying to neutralize some of that acid. So when you do a neutralization, the reaction is always acid plus base, and then that would make water, and then some form of a salt. And the salt can be sodium chloride, but you'll see it can be other things too. So if we were in the building, we would be able to do, this is a really classic chemistry experiment. We would have done actually 2 days of this where we would titrate. And titrating is when you use a burette, and what you do is you know the molarity of this solution that you're putting into this solution, and you know exactly how much you use, so then we know how much volume of this one we have, and then what we can do is then calculate the moles of this solution, and then also the molarity. So if we were in the building, we would be able to do a titration. So I just wanted to show you, and I'm going to kind of fast forward through it, that this is an example of a titration. And we would have used sodium hydroxide in the burette, and then a different unknown acid one time, and then hydrochloric in the bottom another time. So this person's adding a certain amount of hydrochloric acid, and we're going to calculate that volume really carefully because you're going to use that to calculate the molarity of that acid. And then this is the one that you're titrating with. And you would have poured it really carefully into a burette. And then you just slowly add that the one in the burette to the one that's in the flask until you get, you're using an indicator called phenolphthalein. Once that indicator changes color and it continues to stay that color, which eventually happens, and I always tell people slow and steady wins the race here, but eventually when you're adding, you'll get this color to stay, and then that's when you know you've reached what we call the equivalence point. The equivalence point is when, there we go, that's when the number of moles of hydrogen ions or hydroniums equals the number of moles of hydroxide. So if it weren't for the poisonous phenolphthalein and, you know, the fact that we don't eat and drink in the lab, you could technically drink it at that point. So let me just talk to you about a few reactions where you should be able to predict the product. So a neutralization is a double replacement reaction. So we know that the two cations are going to switch spots. And over here, one of these is always water. And it's helpful if you write your water as HOH for balancing purposes. If you want to write it as H2O, feel free. But one of them is always water. Never changes that, the ratio. It's always 1 hydrogen to 1 hydroxide. Then the other part is the salt. And the salt here is sodium. And here's my thinking bubble, you don't have to show this, and chloride. So together, because they're +1 and -1, my salt, whoops, I don't have a charge anymore, I don't know what I'm doing. But the formula for the salt in this case is sodium chloride. Let me show you another one, sulfuric acid and sodium hydroxide. Again, you're going to get water. And then the salt is going to be a sodium ion with a sulfate ion. And again, this is my thinking bubble, and then I know that my formula is going to have to be Na2SO4. So for this one, I would have to balance, and I can see that I'm going to need twice as many moles of base to neutralize this acid as up here, I only need 1 mole per every 1 mole to neutralize. So just some more examples of different, the salt here they put as being blue, and then always water. There are some questions like this where I'm going to have to see if I can move myself out of the way. It's always hard because I go between this tablet I'm using to write. Anyways, here, get out of the way. So here we go. You get to hear my dog in the background again. This is now the salt, and I'm asking you to go backwards and tell me what the acid and the base were. So sometimes when I do this, I'll bring that salt over here. I might even write water, even though they're not asking me for that. But, you know, we know that these are our products. So the lithium, the cation always comes from the base. And then the anion comes from the acid. So what you want to do is, we're going to assume that the base we're using is a hydroxide base. So we would put lithium with hydroxide. This is +1, -1, so that would be the formula. And then the sulfite ion would be in the acid. So then my thinking bubble again is, I know hydrogen is plus, sulfite's -2, so the formula would be H2SO3. So it's possible, if you know the salt, then you know the acid of the base. That's what I'm trying to tell you. And yeah, we could balance it if we want, but we don't need to. It's not really the point of the question. So I would pause it and see if you can try that with this next salt. So the next salt is aluminum chloride, and like I said, this salt, the cation is the base, so we just have to put that with hydroxide, and then the anion is with, that's the acid, so you know the hydrogen will come first. So aluminum hydroxide, so I have to just look at charge, balance charge, and then hydrochloric acid. So notice, whether I'm going from reactants to products or products to reactants, I'm not bringing the subscripts with. I'm always balancing charge. And then I can, at the end, I can balance the whole equation. I think that's all I need. If I needed to, a 3 and a 3, does that work? I think so. So anyways, I'll just show you a little bit more. So as you take more chemistry, what we're always talking about at this point is a strong acid and a strong base being added, but eventually you'll look at reacting and a weak acid or a weak base, and yeah, I'm just gonna let you guys read that and just know that if you're interested, you'll get to see this in AP Chem and then also in your next level of like college chem. So equivalence point, I talked about this when I was showing you the titration video. It's when, it's also called the stoichiometric point. It's when the moles of hydrogen ions and hydroxide ions are equal. And when we do neutralization calculations, we're assuming we're getting to that point, and then doing the calculations. So, so let's show you, I have 2 calculations for you. And these are stoichiometry, like solution stoic problems like we learned in the last unit. So in the question, we have a lot of information going on. So we have 18.7 milliliters of a 0.50 molar potassium hydroxide, and that's going to neutralize. So that would be like what we had used in the burette. It's going to neutralize 35 milliliters of acetic acid. What I want to do is, actually I want to change this not to acetic because that's a weak acid. Let's do plain old hydrochloric acid. So it'll always be a strong base and a strong acid. So we're trying to calculate the molarity of that acid, and this is what we would have literally done in the lab. So first thing we have to do is write the neutralization reaction. So potassium hydroxide plus hydrochloric acid, double replacement. You know that it's going to make water, and then the salt is just going to be KCl in this case. So everything's balanced. Then I'm ready to do the stoich. And with the stoich, when you have all these numbers, you want to start with the volume. You never want to start with the molarity. So I'm going to start with the 18.7 milliliters of KOH. And then I need to convert it right away to liter. And if you want, you wouldn't have to show this. You could just move it 3 to the left. Then I'm going to use that molarity, and if you remember, when I use molarity as a conversion, that really means I have 0.5 moles of KOH in a liter. So I'm going to put the 0.50 mole on the top and 1 liter on the bottom of KOH. So really, I'm using my mole map, and I went from volume to moles at this point. So now I'm ready to do the mole-mole ratio. So I know that I have 1 mole of KOH. I want to cancel that. And then I'm trying to get to the hydrochloric acid. So I would put my 1 mole of HCl on the top. And then I'm going to stop there and calculate just the moles. So this is going to give me the moles of HCl. So my moles of HCl are, what am I, got it over here somewhere, is going to be, my moles, how many moles do I have? I have a dog barking. So I end up with 0.00935 moles of HCl, but I want molarity. So molarity would just be those moles over the liters, which are up here. So I would want to just make sure that's in liter. And then that will give me the molarity, which is, I think, 0.27 molarity. So just to review, I wrote the neutralization reaction. I start with the volume of the one I know the molarity of. I always have to start with the volume in liters. Then I'm going to use the molarity to get to moles. Then I do the mole-mole, do the stoich. And then I stopped because I want molarity. I'm going to plug into the molarity equation. I had the moles, I had the liters from the question. All right, one more. Let's see if I can get there. So this question here is similar but different. It's still a neutralization. You still want to always write the balanced equation first. Balanced equation, it's hydrochloric acid and barium hydroxide. So I'm going to get water, and I'm going to get barium chloride. It's important that you have it balanced, that you wrote these correctly based on charge. And then balancing it, I'm going to put a 2 and a 2. So then the question is they want to know the volume of a 0.10 molar solution of HCl needed to neutralize 25 mils of 0.350. So this is the one where I have the volume and the molarity, and that means I'm going to start with this volume. So just to save time, I'm going to go ahead and convert that into liter first myself. You can also put that conversion if you want, it doesn't matter. So that would get me to liters of barium hydroxide, and then I'm going to use that molarity as a conversion. So I'm going right here, so 0.350, there's that many moles per 1 liter of barium hydroxide. Then I'm ready to do the mole-mole step, the stoichiometric step. So again, so I would put my 1 mole barium hydroxide down here. And then I'm trying to go to hydrochloric acid, so 2 moles HCl here. So I could stop at that point and plug my moles into the molarity equation. I know that it's a 0.10 molar. And then I'm solving, I would put that answer here. And I'm solving for the volume liters, that would be my X. So if I do that, my moles are 0.050. And I'm going to get the same answer as, I'm going to show you, let me just move this out of the way. If I continued, I could continue doing the stoich if you like that better. So I can use that, the molarity, the 0.100 molar. If you think of, again, you have to remember that that's really how many moles of HCl are in a liter. So this time, I would be putting the moles on the bottom, because then it cancels with those, and then 1 liter on the top. So you can do it either way, and then either way, you're going to get your answer in liter, and the answer is 0.50 liter.